Hey everyone, and welcome back to the channel. Today, we're diving into a key concept in analog integrated circuit design: the current mirror. You'll find current mirrors everywhere in analog ICs. Whether it's operational amplifiers, transconductance amplifiers, or biasing networks, these building blocks often rely on current mirrors at their core. That's why understanding how current mirrors work, and more importantly, how to design them well, is absolutely essential for anyone looking to master analog circuit design. Before we dive in, let's go over the key objectives of this session. First, we aim to understand the basic operation of a two-transistor NMOS current mirror, one of the most fundamental building blocks in analog circuit design. Next, we'll design and simulate this current mirror in Cadence Virtuoso. Through a DC sweep, we'll analyze how the output voltage affects the current mirroring behavior, and determine the region where the output transistor enters saturation. Finally, we'll examine how non-ideal effects like channel length modulation influence the accuracy of the current mirror. Let's talk about the most basic form of a current mirror, and it's surprisingly simple. It consists of just two transistors. Transistor M1 is diode connected, which means its gate and drain are shorted. This configuration makes M1 act like a low impedance input for the circuit. The drain of the second transistor, M2, serves as the output of the current mirror. Now here's the interesting part: both M1 and M2 share the same gate-to-source voltage, or VGS. So, if both transistors are identical, same size and same process parameters, then their drain currents should also be the same. This is based on the first-order MOSFET model. Using this model, we can express the reference current Iref and the output current IOUT with these equations. This tells us that the output current can be scaled just by adjusting the W/L ratios of the two transistors. But keep in mind, this is all under the assumption of ideal conditions. In reality, things aren't that perfect. Because of channel length modulation, the drain current actually does depend on VDS. So, IOUT might not match Iref exactly. Alright, so once we've drawn the schematic of the current mirror, the next step is to simulate the circuit and see how it actually behaves. Now, after designing the current mirror using hand calculations, we move to a test configuration, like the one shown here. In this setup, we apply a DC current called IN as the reference, and a DC voltage source at the output, VOUT, which will sweep during the simulation. To get started with simulation, open your schematic and go to Launch ADEL. Now let's choose the output we want to observe. In the ADE window, go to Outputs to be plotted, select on schematic. Click on the drain terminal of transistor MN2, make sure you're clicking the terminal, not just the wire. A small circle should appear around it. Once selected, press Escape to end the selection. Next, hit the Netlist and Run button on the right side of the ADE window to start the simulation. After the run completes, you'll get a plot of ID2 versus VOUT. You'll notice that as VOUT increases, the output current ID2 starts to change, at first rapidly, and then it levels out. That point where it stabilizes tells us the transistor is entering saturation, the region we want for proper current mirror operation. If you want to inspect voltages or currents on your schematic directly, just head to Results, annotate DC node voltages. Or check operating points via Results, annotate DC operating points. These annotations help you understand exactly what's going on inside your circuit at the node level, super useful for debugging and tuning your design.
Thank you for watching.